And we are live. Well, hello everyone, and welcome to today MTech webinar. I am Leo Broca, CBO here at MTech, and I'm really glad to everybody's joining us today in this webinar. The session today is a topic that is deeply technical, but it's also practical in a lot of senses, and it's really needed for today's digital system design, which is called Latency Insensitive Design. We are thrilled to have with us as a host Leandro Echavarria is our speaker. Leandro is one of our top-notch senior digital design engineers. He has a wealth of experience in digital design systems for very demanding applications that goes from radar and software-defined radios up to optical telecommunication ASICs, and also lately semiconductor testing equipment. He has lots of experience and contributed to several projects. For instance, ASML in the Netherlands. He crafted FPGAs, verification environments in SystemVerilog, and also built AXI4 stream-based infrastructure using in high-performance communication systems. Most recently, he's been leading the IC characterization platform here at MTech, delivering the high-throughput FPGA architecture and the SoC system completely. So with that, Leandro, the stage is yours.
Okay, Leo, thank you very much for the introduction. I'm honored to be part of the MTech webinars. I think I need to present myself to see the slides. Oh, there they are. Okay, thank you. Okay, so Leo already did the introduction. I'm a digital design engineer here at MTech, and today we're going to be talking about latency insensitive design, a little bit about the theory, but mainly with a focus on AXI4 stream and FPGAs in particular, Xilinx mainly. So to give an overview of the contents of what we're going to be talking about today, I'm going to start as well with an overview of latency insensitive design theory. It is more of an academic topic in some way. It comes from computer science, so some of the nomenclature is different from what we're used to see. You'll see, and then we will quickly go into some quick comment about industry adoption and focus on axis stream on rules. Some waveforms we're going to be showing. Then I'm going to talk about some infrastructure, a little bit of a code example by ourselves. Then some talk about a suite of IPs by Xilinx, which is very useful when you have to build a complete SoC on Xilinx FPGAs. And lastly, we're going to show some code examples in SystemVerilog for an interface for AXI4 stream, some assertions inside the interface, and a very trivial implementation of a finite impulse response filter. Okay, so to be sure that we are all on the same page, we're going to be talking about digital design. This is the level of abstraction, usually RTL. Our focus is mainly on FPGAs, but this also applies to ASICs. The other very important abstraction is that we talk about synchronous design, which is a very important assumption for building digital systems in the last 4 or 5 decades or so. What was encountered around the turn of the century was something called by the academia as the wire problem. This was mainly developed by Luca Carloni from Italy, which is one of the main researchers in latency insensitive design. And I'm going to refer to a number of papers by him during the presentation. The idea is that while the transistor count inside ICs has trended upwards, and also frequency for decades, the delays in the interconnects saw no speed gain in the same measure, partly due to capacitance, but the result is very clear, is that the smaller percentage of a die, whether it's an FPGA or an ASIC, is reachable within one clock cycle. And when this happens, the assumption that you're synchronous falls apart a little bit. So it's very difficult to synthesize designs, because as you see this picture below, a very common explanation of static timing analysis, this cloud of combinatorial delay you start to have to take into account the delay of the interconnect as well. So this makes, of course, timing closure much more difficult. To give an actual example, it's estimated that a relatively modern device, such as the Intel Stratix 10, achieves something like 100 megahertz register-to-register frequency when you have something floor planned from each end of the chip, which is probably 5 or 6 or even 7 times slower than what's the usual frequency, the max frequency you can achieve with this kind of device. So this means that it takes maybe 5 or 10 clock cycles from a register on one end of the FPGA to reach the other end. So what these people proposed as a way to reconcile synchronous design with this modern problem, the wire problem, is something called, well, the latency insensitive design, which as a paradigm, it allows a clear separation between computation and communication. Mainly, the theory says that you can consider two systems as latency equivalent, as it says here. If in every channel they present the same data streams, pretty much, I mean, the same order data, but possibly with a different timing. I put a picture with an example of some signals which are considered latency insensitive, latency equivalent. Sorry. The reference signal, which is usually called strict signals, has no bubbles or idles, and you will see that every clock cycle it will present a new data vector. But if you have a separate signal which can also carry metadata indicating whether the data in that instant, in that clock edge, is valid or not. In this case, this is mentioned as a stall, but you will see that the stall is pretty much the inverse of a valid. Both the second and the third signals that I show here are considered latency equivalent to the first one, because even though the timing is different, they present exactly the same set of ordered data along the time, even if the throughput, the bandwidth, is not exactly the same. So okay, this is a little bit too loaded, the slide, but to quickly tell about the how, what they present is a classic way of solving this, not only a description of the problem. Is they usually, Carloni and others that have investigated this, they propose two modules which are a core of this methodology. One is a shell, which is a wrapper for your core module, and that this will adapt your core process into the latency insensitive design protocol. There's some naming there. Your Perl or your core module has to be tollable, which pretty much means that it should work with a clock enable, and it shouldn't. You should be able to just stop it and nothing, no data is lost and no state is lost as well. And this wrapper adapts everything into a clock enable, and it also presents buffering at the input. The example below to the left is one of his papers. It's actually a shell for 2 input and 2 output device module. And just a quick comment, because we're going to be talking a lot about axis stream. What this here is referred to as stopping, it's actually the inverse of what we consider the T-ready. It's an input that's coming from downstream, and the void in is pretty much the inverse of the T-valid, which is an input coming from the module upstream. The other very important module, it's what they call a relay station, which is pretty much a 2-deep buffer that presents a way for us to introduce some kind of pipelining along the interconnect data paths in these kind of protocols. Because the thing is that if you have to deal with back pressure, you will quickly realize that you cannot just register every signal because they're going in opposite directions. If you do that, you will be subject to losing data. If you're doing very low throughput or atomic transactions, that's okay. But if you have something that has to achieve full throughput, you cannot just register, because whenever it stops, it can lose data. Just a very quick comment, but Avalon streaming supports something called ready latency. All right, sorry. Avalon streaming supports something called ready latency, which pretty much allows for these kinds of situations to happen. And you can tell the system that you have some registers along the ready path, but axis stream, which is going to be our focus, does not support that, and I think it's better that way. The relay stations, which is what you see below on the right as the example from the paper, they sometimes are referred with different names: Carloni buffers, skid buffers, or register slices as well. Maybe the implementation might not be exactly the same, but what they want to achieve is usually the same. You have to cut the combinatorial path, so you can achieve better timing. There is just a small caveat. You will see that the stopping signal in the original Carloni buffer is not registered. You will see that it goes through a combinatorial FSM, and that's also not ideal. So, sorry, to summarize some of the pros and cons with latency insensitive design, I think some of the pros go beyond just solving this wire problem. because some of this, it's actually good for modularity and system design in general, because the fact that you are separating communication from computation is actually quite a good idea for both design processes and for verification as well. You can, if you define have a well-defined set of rules, such as using a standardized interface, you will see that you should be able to hook up designs that follow the same protocol together, and they will work because of this correct by construction composition. Because the designs are latency insensitive, you can add pipelines, and the synchronization will not be lost. So yeah, going over the items here, I mean, you can say that the pros are you have some modularity, which reduces coupling and also allows for decentralized synchronization. Not going to talk about that, but it might come up in some questions. Scalability, what I said about correct by construction, efficiency in general, because a well-defined set of rules make it easier for reuse IP. And well, pretty much the conclusion from the first paper is that beyond achieving a way to close the insert pipelines and close the combinatorial paths, you can also relax the timing constraints during the early phases of the design. This is something even, I think, more relevant for ASICs, where there's really not a lot of information about what the routing is going to be looking like in the early stages of the design. And if you have any problem down the line, it's much easier to adapt by introducing relay stations or pipeline stations of some way. As of the cons, we could say it incurs in albeit small area overhead. This depends on the implementation. It adds complexity from managing back pressure, and it may incur in performance overhead as well. And this also depends on the implementation. We will talk about a little bit about that later on. So the industry adoption, once we switch from a nomenclature coming more from academia to something that we're probably more familiar with, we can say that there's been a number of commercial protocols since this was presented the first time. Well, I didn't mention it, but the original Kaloni papers come from his PhD years in I think 1999 or 2000. So it's been quarter of a century already. And since then, we've seen an emergence of a number of commercial protocols that adapt these basic assumptions of latency insensitive design, even though they, of course, implement it using their all flavors. Probably the most famous ones are the ones coming from ARM inside the AMBA protocols, Axie3, Axie4 Stream, which is going to be our focus. The separate channels of Axie4, Axie4 Lite, are pretty much very similar to Axie4 Stream channels. Axie5, which I haven't worked with pretty much, but is an evolution of previous protocols. On the Intel side, the read and write data channels for the Avalon memory mapped has implements these kinds of signaling, and Avalon streaming looks a lot like Axie4 Stream in a number of ways. beyond the basics, it starts to differ a little bit, but it's not a big deal. I put just an example as TileLink from Sci-Fi as another commercial protocol. So we can start talking about the specifics of Axie4 Stream. Sorry. This was introduced by ARM in 2010 as part of the AMBA4 specification. If I'm not mistaken, I think it was commissioned to Xilinx, or so I heard. But what we do know is that it's been widely adopted by Xilinx since their first SoC devices, the 7 series syncs, and the transition to Vivado. And it's probably, yeah, the AMBA4 is probably the main bus chosen by Xilinx to implement their block designs in the FPGAs, but mainly also for the connection. I mean, there's to the hard processors, because the connections to the PS has a lot of hardened buses. They are all different flavors of Axie going in different directions. So to describe Axie4 Stream specifically, it is a point-to-point protocol. It's synchronous. So we say that both the transmitter and the receiver use the same clock. The names changed not a long time ago. They used to be called master and slave. Now they are referred to as transmitter and receiver. So it specifies a number of signals. Not all of them are, some of them are optional. You have a clock, which is global because this is synchronous. You have a reset, which is active low. The main signals are the ones that indicate the handshake. So that's why they are in bold. You have a T valid, which goes from the master to the slave, a T ready, which is the back pressure signal going upstream, and then the primary payload, which is the T data. The rest of the signals are, many of them are optional, and the handshaking process, they act a little bit as metadata because they have to be transferred in the same, pretty much the same cycle as what T data would do. You have a couple of byte qualifiers, the throw and the keep. The T-last indicates boundary of packets. This is used quite a lot. Then for identification and routing, you have TID and TDEST. And a user-defined sideband is T-user. So there is a number of protocol rules. This is taken from, okay, I forgot to put the reference here, but this is all taken by the Axie4 Stream. Now it's merged into the Axie5 Stream document by ARM, the reference document by ARM. You can just Google it, and you can access it freely. The rules come from there, and they are summarized here. So, well, one of them is that the data web has to be an integer number of bytes. To compare with Avalon, this doesn't happen in Avalon because you can define what your symbol is going to be looking like. The symbol can be a byte, as in Axie Stream, or it can be something else. Probably the most important one is that the transaction occurs if and only if both the T valid and the T ready are asserted in the same rising edge of the clock. I will show some waveforms later on to make this clear. Some rules about the T valid: it must be asserted as soon as there is data available. If you have data to give, you have to assert valid. And as a rule, you cannot wait on the status of the T-ready. So T-valid has to be completely independent of what T-ready is doing. T-ready, on the other hand, can wait on T-valid to be asserted. So the master has to assert T-valid as soon as there's data, and the slave can wait or not to assert T-ready to indicate a transaction acknowledged. This is mainly, well, to avoid channel deadlocks, but also helps with routing. Another rule is that the T-valid, once it's asserted, it has to remain high until the data has been transferred. You cannot toggle T-valid high and then low if the data has not been consumed by the slave, unless it was the case of a reset, which is a signal that's shared between master and slave. The T data as well must be stable until the data has been transferred. And the same applies to every extra data bits and qualifiers and sidebands, etc. There is a couple of rules about the reset. It's, well, very classical from I mean, this comes from ARM, so from ASIC design, asynchronous assertion, optional, but it must be deasserted synchronously. And the T-valid must be driven low during the reset. It may be asserted again in the following rising edge clock after the deassertion. The other signals can be driven to anything. That's it. It doesn't matter. There's another rule that people talk about a lot, which is that the T-valid shouldn't have a combinatorial loop between T-valid and T-ready. But during my research for this presentation, I found out that this doesn't appear in the Axie4 stream spec, but actually it's part of the Axie specification. So I don't know if this may be actually disputed or not, but just a color note. Okay, I talked a lot about the rules. We can go back to that slide more than once. There's no problem with that. But I think it will be easier to see what I'm talking about if we see some actual waveforms. The first one we see here is an example of a valid Axie4 stream packet transaction. You can see I only included the clock, the reset, valid ready, and data, and also the TLast because it was interesting to see as well. To notice in the waveform, you can see that, well, first of all, the T-valid, in this case, it's asserted independently of the T-ready. It's also not asserted during the reset or following cycle after the reset deassertion. One thing that's a common problem when people deal with Axie stream is that they change data when they shouldn't, and you can see here very clearly that the data is the T data is only changing after valid transactions. What I did here is I introduced some kind of toggling in the T-ready. This would be similar to a downstream module introducing some kind of back pressure, and you will see that the T data is actually kept stable for 2 clock cycles for D0, D1, and D2, because there's only one valid transaction for each of them, and then T-ready goes high continuously after D2. And D3, D4, and D5, the transactions, they take only 1 clock cycle. But if you count the positive edges, they're only transferred once. TLast here is is also considered like an extra bit of data. So it has to go high only for one clock cycle because that's what it's conveying. Below you can see 3 timing examples taken from the specification. What can actually happen is that the handshaking can take any of these 3 shapes. It really can happen that the t-valid is asserted after the t-ready, as in figure 2.2, the one in the middle. But if that happens, it means that the valid it just happened to go high in that moment. It doesn't mean that it was waiting for the t-ready. It cannot wait on the t-ready. But all of them are valid transactions because they are transferring data. In 3 cases, they are transferring data only once. Okay, so just a quick comment about the byte qualifiers. They the t-keep is usually used to indicate which of the bytes inside the signal contain valid information. And to do that, well, the t-strobe, whether it has to be all high or I think not used, you will see that the width of the t-keep is equal to the width of the t-data divided by 8 because it presents 1 bit per each byte of data in the t-data. So it's common to see that the t-keep will be telling the downstream module which of those bytes you want to keep. But if you use this truth table, if you use the strobe in another position, the t-keep can also be used to indicate position instead of data. This is mainly used when you want to do some kind of interleaving. Something to note, which comes from, there is a document by Xilinx with details the how many of the things in the protocols they are actually accepting or taking into their designs, and they chose to only listen to t-keep at the end of the packets. And if you have a stream, if you toggle some of the bits in the t-keep in the middle of a packet, the AXI models from Xilinx IPs will not pay attention to that. So it ends up working a little bit like the empty signal in Avalon streaming. Maybe some of you are familiar with that one. Okay. Going to talk a little bit about infrastructure already. This here is just a quick example of a skid buffer, but fully registered. First of all, it becomes trivial when you try to do it, that if you just register, if you build a rather trivial register stage for AXI stream, and you want to avoid losing data, which is why I told you about before, what you have to do is alternate between receiving data from upstream and transmitting it downstream. This, of course, means that you only supporting this kind of slice, you only support 50% throughput. That's why the trivial register stage for AXI stream is called a half buffer. But the example I give below, it's actually a skid buffer that's fully registered. Don't really pay attention to the schematic. The only thing I wanted to convey here is that you can see that the ready, the valid, and the data going out are coming from flip-flops. So the combinatorial path in the 3 signals is being cut, and this of course is the best case scenario for when you want to achieve higher frequencies, or you're having trouble closing timing. There's really the code example on the left, on the right, I'm sorry, is exactly the same design, and the idea is the same. So you can see that the data, the valid, and the ready, they're all implemented inside an always flip-flop block of SystemVerilog. So yeah, they have to be synthesized into flip-flops registers. There is a pretty much an equivalent of the skip buffer inside the catalog of IPs by Xilinx, which is called AXI register slice. It also supports AXI4 and AXI4 Lite, but it pretty much carries the same. It does the same. You can see in the description that it says this is taken from the IP user guide. The most important thing is that it says the same as what I was mentioning before. This is fully registered. It's implemented as a 2-deep FIFO buffer, which you can see in the previous design as well. You can see that the data has 2 flops, a main one and an auxiliary one. So this is telling the same thing. It allows up to 100% duty cycle, so you can deal with having no bubbles. Bubbles and stall cycles are pretty much the same, right, inside the data path. So next, the idea is to talk. I'm sorry I didn't say it at the beginning. We just started, but I think is 20 to 12 here. The idea was to talk about the slides first for maybe 45, 50 minutes, and then hopefully answer some of your questions. So you can leave your questions in the chat. So I have some minutes left, and I have some slides left as well. So let's keep going. There's a suite of IPs by Xilinx described in PG 85 by them, used for interconnect purposes. I mean, it does not include any description of processing modules. It's not going to show any sphere, a filter, or whatever, or DMA or FFT. Intel in the Quartus or QSys systems, it provides a similar set of IPs for avalanche streaming, even though they are adding support for AXI as well. And the list of cores described in this PG, in this infrastructure suite of IPs, is the following. There's like a basic set of 8 cores, and then the interconnect is actually composed dynamically of the ones before. I'm going to talk a little bit about the ones in bold, but you have a broadcaster if you want to replicate signals from one to many. You have clock converters, which are very important if you want to do CDC without buffering. You have combiners, which should be some kind of opposite of the broadcaster. You have a data FIFO, not to be confused with AXI Stream FIFO, which is another IP you can use in Vivado. You have a data width converter. You have the register slice, which I mentioned before. You have a subset converter, a switch to route signals, and an interconnect, which is has a switch at its core, and it's a combination of the ones of the ones above. So the Axie4 stream data FIFO is probably one of the most useful ones. I put here a small image coming from Vivado. You're probably familiar with this to show the ports. It also supports dual clock operation, so it does CDC if you want it to. It supports packet mode, so it can actually be a very deep FIFO if you want to do store and forward, which is useful for interconnect sometimes. It's the kind of memory it uses. It's also selectable between distributed and block RAM, and if the device supports it, also ultra RAM, and it also has some extra nice extras like error control and some data counts modules, like some data counts ports like the ones you see there. The clock converter also supports doing CDC between a master and a slave, but without buffering. It's only going to give the amount of stages that you need to synchronize. If it detects that the clocks are synchronous, I mean phase aligned, and then they have an integer relationship, it's going to do some kind of more efficient CDC as well. Otherwise, it's going to go fully asynchronous. And what I say here, I mean, this is taken from the PG. I found this interesting. It says that the infrastructure IP should be clocked at the same rate as the fastest slave. So ideally, you have to convert everything else. And the synchronous clock converters are ideal because they're more efficient. Something to notice is that the conversion is done from a fast to a slow clock. The module will produce back pressure, right? I mean, what you deal here is you're not losing data, but you're going to stall the data path because this does not convert any kind of width, right? So if you're entering with something that's 100% throughput, 100% duty cycle, and it's going to a slower clock, there's no other way but to introduce back pressure. The width converter can be used both as an upsizer and a downsizer. It's and this is very straightforward. I think I should pick up the pace a little bit. You can build a gearbox if you combine a CDC data FIFO or clock converter and a width converter. A gearbox is usually what you call something that's when you interchange frequency with bus width, right? So I don't know if you can read it here, but in this example, there's the throughput at the ends is both 100% duty cycle and the actual throughput is the same, right? But on one case, we're entering with 200 megahertz and 128 bits with wide bus, and the output is going at half the frequency rate, but double the bus width, and it's still using 100% duty cycle. In the middle, you would actually have to go wider with a width converter and then go slower with a clock converter. Very quickly about the interconnect. It uses a switch at its core and it supports different types of routing. You can route according to tdest, and you can build the routing table for in synthesis. And there's also a mode, if I understand correctly, to route using control register interface, and it will automatically introduce all kinds of adapters for widths and clocks in what this is called here, the coupler. So this shouldn't be here. Okay, we can go over a little bit some code examples, and I'll try to be quick, and then we can go over a couple of questions. What I wrote here is a very quick implementation for demonstration purposes of the Axie 4-stream interface in SystemVerilog. You will see, well, I have a to-do in line 2 of to enable some optional signals, some enables to the signals that are optional, because otherwise I'm including them all. But you will see pretty much that I'm using a package to define the parameters for each signal. This is coming from outside. And the list of ports is very short, right? You're having only some parameters, and then, well, an input of a clock and the reset. That's all. And then inside the interface, you define all the signals I mentioned before. And below, you define the mod ports, which is when you the same interface can be used both for masters and slaves. So you define like 2 directions for the same set of signals, which are pretty much opposite, beyond the clock and the resets, which are always inputs, of course. So using this interface, I wrote as an example a fill filter. I wanted to actually mention this one as a very short list of ports, because you will see that I only have line 6 and 7. This is the input and the output, and the clock is actually included there. There's no way to tell that the clock is the same in both interfaces. There's maybe a limitation of the SystemVerilog interface implementation, but I'm giving as a parameter a data type with the coefficients. And pretty much what I'm doing here, which you can see in the comment below, is I'm introducing skip buffers to break timing at the input and the output. To do this, I have to define 2 extra interfaces. To the input SB phase is what I use in the design below, and the output SB phase is what I use as an output. So the module logic will fall between those 2. Something really important here is that, okay, the acknowledge of the transactions, this is very useful to have these auxiliary signals that you see in line 28 and 29. The acknowledge of the input transaction always means valid and ready at the same, both asserted. And the same happens for the output transaction. Then how you connect things depends on what you do inside the module, right? This is what follows in the code. You can see here, I mean, the first part of the left is not really important. I just wanted to tell the output value to pretty much not be valid, well, when the first part of the pipeline is flushed, because it's going to have data full of X's, and that's not allowed per protocol. But pretty much the line 64 and 65 is that I'm actually connecting the T-readies together and the valid together. So the advance of the pipeline, I can say that can be done with the input transaction acknowledge. So I'm using that one in line 75. I say enable signal for line 80, and then on the right, line 91 as well. I'm actually advancing the delay lines and the summation lines with that enable. Okay, and I think this is the last part. I included in the same interface below a number of concurrent SystemVerilog assertions, which are, I think, a very nice addition to Verilog when SystemVerilog was introduced to support having some kind of checks in synthesizable code. This is not taken into account by the synthesizer, but you can introduce it in synthesizable code, and when you run simulations, this will actually fail if something's wrong. So it's nice to have a set of assertions inside the actual interface that's used everywhere for your IC stream device modules and infrastructure. The rules, many of them are the same. I mean, it's that the data must be kept stable if there's no transaction. We saw that before in the waveforms. So this is what it's actually telling, right? I mean, if you want to see a little bit about SystemVerilog assertions, the syntax, there's a really nice Dolos tutorial that you can find very quickly in Google. So I'm pretty much actually telling, okay, if this is not in reset and the valid is asserted, but there's no ready, next cycle the signal has to stay stable. The last couple of ones are related to the reset for the valid. And the last one is that the data does not have to contain any X. I mean any unknown data within the vector when the valid is asserted. This actually has to go for every signal in the interface. But yeah, as you saw before, I don't have any enable parameters for the optional signals. So if I check that, it was going to fail. So okay, I have a couple of minutes for some questions. I want to thank you everybody for listening to the presentation and for tuning along. I want to of course give thanks as well to Gasti, Maya, Leo, and Fiona for your help with preparing the presentation, and it's been yeah.
Okay, thank you, Leandro. Thank you very much. That was a brilliant presentation, a brilliant walkthrough of both the theory and the application. It's clear that in all of your experience and having hands-on on HDL development, this gives this presentation a real world edge point of view. So why this topic is so important for us here at MTech? I'm going to let you give a little peek behind the curtain. So we were talking yesterday with Leandro and Gaston, our CTO, regarding this presentation. And we agree that in today's digital design, you cannot assume that everything runs under a single clock. And within the larger and larger FPGAs, all the interconnection delays within the chip often exceeds those clock periods. So that forces us to rethink how we design, and that is where the information that Leandro provided us today is so helpful. So thank you again, Leandro. This kind of things aligns perfectly with the kind of work we do here at MTech, which is developing IP and particularly in ecosystems using AXI4 stream, which is today the industry standard. So thank you again, Leandro. And now it's time for having some questions from the audience. Let's go with the first one, which is it should be popping up on the screen, I guess. Yeah. How do you deal with the systems that do not support back pressure, including ADCs, DAC, and transceivers?
Okay. Yeah, it's very common for we deal a lot with data paths that at the edges they do not support back pressure, because you're dealing with interfaces that go pretty much they go beyond the chip, right? I mean, and they have to have something every clock cycle. Something we're quite familiar is, for instance, in the case of the both the IDCs and DACs, you have to make sure that you can, in the case of the DAC, you have to make sure that you can produce data every clock cycle, right? You have to achieve full throughput at the edge. And the same in the case of the IDCs, you cannot back pressure. So if you don't get every data every clock cycle, you're going to lose data. So in the case of the DAC, it's quite, both cases, it's quite usual to go to maybe a faster clock that gives you some slack and pretty much a buffer. Also, you sometimes deal with going from wide buses to narrower buses when you go into DACs, and the other way around when you're dealing with IDCs. That way you can consume data with different access patterns, and your valid ratio can fall below 1 without incurring in data loss. I hope that that answers the question a little bit.
Yes, perfectly clear. Yeah, wonderful. And now for the second question, what are the main challenges when implementing latency insensitive design in FPGA environment versus the ASICs?
Okay, that's a challenging one. My experience with ASIC design is much more limited, of course. So take this with a grain of salt. What I remember is that what I was usually told is, as a rule of thumb, usually flip-flops are cheaper in FPGAs, and they're considered more expensive in ASICs. And maybe the other way around for combinatorial logic, because the granularity is very bad in FPGAs in terms of LUTs, and the combinatorial things you can build in an ASIC is much finer. So what I've seen in some designs in the past is that in ASIC design, they do implement some kind of latency. I think you can still call it latency insensitive, because they use a valid signal, but they do not use a ready signal. That way, it's easier to register the data path, because the register slices are trivial. You do not have to make use of a real station. But what I've seen also in the past is that they only register the valid signal. This is what I'm telling you, that take with a grain of salt, but because I think this only applies to resyncing data paths, and sometimes that have a transient state which you do not care about, and so you're actually using the valid from the previous data to transfer. That, I think, that works in some cases. That's, I think, everything I can say about that, because, as I said, it's my experience there. It's a little bit limited.
Yeah, it's a lot to say. So thanks again for the answering. I think we have room for one more. There are some recommended open source libraries to work with VHDL and Verilog.
Yeah, definitely. Sorry. I think what comes to mind quickly is there's a set of libraries by a man called Alex Forensich, which has a good set of I think he built a network IP called Conundrum, and he published a lot of IP in GitHub for Axie in Verilog mainly. I think that's a good result. Anyhow, we're going to be uploading the presentation as well as some examples of code to GitHub, to the MTech GitHub. There's going to be a repository there. Shortly, we'll probably share that in LinkedIn soon, the next couple of days. And actually, there's another slide which has every reference I use, because I get numbers for every reference. That's after the thank yous. And you can also, yeah, you can also see there where I took the information from. SIP CPU is also a very good source, and also there's something called FPGA CPU.ca, which is a site by Eric LaForest. Is a great resource as well. But I'm going to write those down in LinkedIn in another moment. Yeah.
Okay, excellent, excellent. And the last one, we have one last question, which is it mandatory to use this workflow into a DSP chain? Or maybe it's just a good practice?
I mean, of course, nothing is mandatory. There's a reason it's been used so much lately. If you have no kind of valid data or valid signal along a DSP chain, you have to balance the latencies pretty much manually along the path. For instance, if you add pipeline stages and you're only counting clock cycles, and you add a register stage, pretty much the modules downstream have to know about that. So I think the system in general becomes really coupled, and it's very difficult to design and to verify modules separately if you don't use any kind of valid and ready, at least valid signaling. So I think it's good practice, and yeah, maybe just deal with the fact that some systems really need to deal with. Leo has a lot of experience with that. In radars, you need to make sure that the time is correct for phase coherency, for instance. But you only have to deal that at the edges, right? When you're accessing DACs and ADCs. Then if you have enough throughput and the jitter of your data path is okay, it's my recommendation is that you use some kind of latency insensitive design. It doesn't have to be axis for stream. It can be something simpler, like only a valid or only a valid ready handshake, which is not up to spec or whatever.
Yeah, as always, knowing the stuff, knowing the technology is a useful tool for the rest of your design and to have results. So thank you again, Leandro, for the answering. And I guess this is the last question. This was the last question. So that concludes today's webinar. So thank you all for joining us. If any one of you would like to revisit anything from the presentation with all the updates that Leandro will add shortly, we will put it online. Also remember, we had another wonderful seminar before given by Maya regarding verification in UVM, so that is available also. And if you're working in digital design systems and you want to explore how these techniques may apply to your architecture or your projects, please feel free to reach out to me or Leandro or anyone on our team, whether it is an IP integration or you need to verify something, verification strategy, or high-speed FPGA developments. We are more than happy to collaborate. So thank you again. Until next time, and all the best.
Thank you everybody, and yeah, a quick thank you to my friends from my time in the Netherlands, which I know that some of you have joined. So yeah, that was really nice. So yeah, thank you as well.
Goodbye.
Thanks.